Okay, hello everyone and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today we have the honor of having Dr. Tessa Baker from the Queen Mary University of London. Dr. Baker is a physicist working primarily on gravity and the complex role it plays in shaping our universe. Her work focuses on a broad range of topics such as dark energy and modified gravity, gravitational waves, galaxy surveys, and the large-scale structure of the universe. She's a principal investigator of the SHADE project, which aims to develop the future techniques of gravitational wave cosmology to shed light on the nature of dark energy. She's also an active member of the Rubin Observatory Legacy Survey of Space and Time, the ESA Euclid Satellite, and the Laser Interferometer Space Antenna, so LISA. Dr. Baker, thank you so much for being so kind and having accepted to give us a webinar talk today on such an interesting topic. The floor is yours.
All right. Thank you very much for the intro, Tessa. I'm coming at you from my office at Queen Mary in London. It's just gone 6 p.m. here, so it's sort of starting to get dark. It's a real pleasure to be talking at you from a distance and telling you about my work on gravitational wave cosmology. And in particular, the story I want to tell you today centers around what we can do with gravitational waves, but without electromagnetic counterparts. And I'll explain why that's sort of an interesting thing to study, why it's relevant to the next few years of gravitational wave science as we go along. I should say, because I'm in presenter mode, I can't see any of your faces or your boxes. So if you have a question, it's that awkward thing where you just need to unmute and interrupt me, and I'm totally fine with that. I think that's the only way to do it. Okay, so before we get into the talk properly, oh, there we go. I thought it was worth sharing with you this sort of rather nice graphic that's been made of the current gravitational wave detections we have. And it's sort of presented like a periodic table. The colours of the different squares indicate the observing run in which the gravitational wave event was found. So starting with O1 here in the top, the first observing run, O2, and then you can see the majority of the events here happened in the two halves of the third observing run. So that's O3A and O3B. These are the observing runs of the LIGO detectors, or LIGO Virgo Cagra detectors. For each event, what you are seeing in the two corners are the progenitor objects, so the things that are in that compact object binary, and their masses. And then in the center, you're seeing the remnant object that is formed after these two black holes or neutron stars merge, and its mass. So black is a black hole, and most of the things on the figure are black. But if you look closely, you can see a few blue points. Those are neutron stars. And just in a couple of places, there are things that are sort of half black and half blue. And that means we're not completely sure whether it's a very light black hole or a very massive neutron star. It's hard to tell. So this is everything we have, but let me point out perhaps some of the highlights of this catalogue, some of the most interesting events. So the most massive binary black hole merger that has been detected to date is this one over here, 1905-21. And it's notably, I've put under here, the most massive confident detection, because you might notice this one here is actually more massive by numbers. However, this is a less confident detection. So when the LIGO Virgo Cagra detectors detect something, they produce this kind of probability breakdown for what they think the object is, where at the top you've got binary black holes, in the middle you've got NSBH, neutron star black hole, At the bottom, you've got BNS, binary neutron star. There's something here called the mass gap. We'll come back to that later. And there's this thing saying terrestrial, and that basically means it's not a real detection. It's a false alarm caused by something going on the detectors or something on Earth. And so for this event here, there's over a 99% probability that it is a real astrophysical event, whereas for this guy over here, where there's a significant chance it's actually a false alarm. So similarly, the nearest binary black hole that's been detected to date is over here, 170608. The first confident neutron star black hole detection is this one down here, quite late in 03. And of course, the poster child of gravitational wave cosmology was the first ever binary neutron star detected and the first and only standard siren to be detected. And we'll explain what that means in a moment. 170817. Okay, and many of you will have been aware of kind of the big press releases and things around the time of this detection. And actually what this figure shows is how lucky we were to get such a spectacular event so early on in our gravitational wave detection story. Okay, nothing more spectacular kind of happened in all of the third observing run. So this is the data we have right now. And what I want to do today is dive a little bit deeper into how we use this data to answer questions in cosmology, particularly things like constraining the Hubble parameter and tests of gravity. So here's what we're going to do. We'll start off by talking about what standard sirens are, why they're exciting for cosmology, but also some of the challenges around them. And I want to convince you that there is perhaps a need for an alternative to standard sirens, which goes by the name of dark sirens. And again, we'll explain what those are and how they work. And then finally, depending on how time goes, at the end, I'll talk about how all these kinds of events help us perform tests of gravity on cosmological distance scales, and in particular, how we can do that without electromagnetic counterparts. I should say that, of course, much of the work that I do depends on my fantastic team here at Queen Mary. So here they all are. And many of us at Queen Mary, and much of this work is done in involvement with particular collaborations. For the things I'm talking about today, the two most relevant being the LIGO scientific collaboration and the LISA consortium. Okay, so let us get started with the standard siren case. And today our definition will be very simple. We'll say that a standard siren is a gravitational wave event that has an electromagnetic counterpart of any kind. Okay, I don't care what part of the frequency spectrum it's coming from. And the standard case for this would, of course, be a pair of merging neutron stars. We know in that process, which is very messy, there's some very high energy gamma rays that can be produced, and we know that then fades across the EM band down into longer wavelengths. However, there is a possibility that there may also be standard sirens from massive black hole mergers. So if you have two massive black holes at the centers of galaxies, when they merge, there is a lot of gas at the center of a galaxy. And there's a lot of ideas saying that some of that gas could be shocked and heated in a way such that it also will produce some electromagnetic signature. However, until the LISA mission flies and we actually detect the merger of these massive black holes, no one really knows for sure. So whilst I flag that possibility, today we'll really be thinking about the kind of regular binary neutron star mergers. Okay, so why are these things exciting for cosmology? To explain that, I've got an expression on the slide which shows the amplitude of a gravitational wave coming from a binary system. And this could be either the plus or the cross polarization, which are the two modes of the wave. So this wave amplitude depends on, and I've dropped all the constants, It depends on something called the redshifted chirp mass of your binary. That's a particular combination of the two masses involved with a factor of redshift. It depends on the frequency of your gravitational wave to some exotic power. And then there's a bunch of angular factors that describe something to do with the polarization of the wave and its orientation of the source on the sky. But what we really care about today is this distance which sits in the denominator, and that's the luminosity distance. And the luminosity distance is one of our standard distance measures in cosmology. It's given by this expression in terms of redshift. So there's a factor of redshift, and then there's an integral which depends on the Hubble function. And the important point here is that the Hubble function contains the most important parameters in cosmology. So I have a simple example here on the slide. This is for a universe that has some kind of non-standard dark energy component. So there's the Hubble constant, h0. There's the matter fraction of the universe, omega m. And if you've got some exotic dark energy that's not just a cosmological constant, the equation of state of that also appears in this function. So if we can get access to both sides of this equation, if we can get the luminosity distance and the redshift, we have a way to access the parameters sitting in here in a manner that's sort of independent of and different from some of the other probes in cosmology, like the cosmic microwave background. And standard sirens are something that provide us with exactly that opportunity. So that luminosity distance is something we can infer directly from the wave itself. If we see an electromagnetic counterpart, and here you're seeing the Hubble picture of the counterpart of 170817 as it fades over about a week. If you can see a counterpart, you can put a spectrograph on that, you can get a measurement of the redshift, and hey presto, you've constrained both sides, both pieces of that luminosity distance redshift relation. That means you can access, for example, the Hubble constant, you can measure your h0 parameter, and maybe if you get really lucky, you can solve the Hubble tension with some new piece of information that's independent of current probes. And if you can do that, of course, fame and prizes and glory await you. Okay, so this is why standard sirens are getting a lot of press. So no surprise that the LIGO-Virgo-Cagra collaboration tried to do this with 170817, the first and only standard siren. So this is their result. So what you see here is their posterior for the Hubble constant. And in orange is the measurement from the local distance ladder, effectively. In green is the Planck measurement. And you can see that the LIGO measurement peaks ever so diplomatically right between those two bands. However, because of the width of this posterior, there isn't actually a competitive constraint just yet. Right? We've only got one data point. Unsurprisingly, the error bar is of order 10 kilometers per megasecond. Excuse me, 10 kilometers per second per megaparsec. So it's a good first kind of proof of principle, but it hasn't solved the Hubble tension. Okay, but you can get the idea that if we had many more of these things, we'd be in business. That's not all you can do with standard sirens, though. In a manner I'll explain a little bit later, if you have a departure from general relativity on cosmological distance scales, that can also change the luminosity distance redshift relation. And that again is something you could test with standard sirens. So again, you've got the ability to detect or constrain deviations from GR, and that's obviously another very high impact area for cosmology, where you can win your fame and prizes and glory again. Okay, so for all these reasons, people love standard sirens, even before we've started thinking about all the interesting astrophysics that comes out of them. However, things aren't completely straightforward. So in order to get that percent level constraint on the Hubble constant, you can estimate we'll need something of order 100 standard sirens. Okay, it might be a bit more, might be a bit less, depending on where those sirens are, but something like that. Problem, the rate at which standard sirens occur, or at least detectable ones occur, is unknown. We've only had one data point so far. We really struggle to measure the rate with one data point. So should we just wait? Should we just sit here and wait for standard sirens to filter in? And I want to try and argue, unsurprisingly, that the answer is no. And there's a couple of reasons for that. First of all, if you just wait for standard sirens, which we believe are binary neutron star mergers, you are ignoring all the incredible data we have coming from binary black holes. Okay, probably lots of you have seen a version of this plot showing the current detections now kind of as a function of mass. Everything in blue is a binary black hole, and at the moment they vastly outnumber the neutron stars. So why throw away all this data? Secondly, electromagnetic counterparts by their very nature are most detectable at low redshifts. And that's fine if you want to constrain the Hubble constant, which is something you can do at low redshift. But if you want to do those tests of gravity, that's something which really benefits from having access to higher redshifts. And again, we'll kind of make this clearer later. So, how are you going to do that with standard sirens? And finally, we really have no idea, or very little idea, how long it could take us to collect enough standard sirens. So call me impatient or maybe pessimistic, but I think it's worth asking ourselves, what could we do in the meantime without those electromagnetic counterparts? What can we do from gravitational waves themselves? Okay, and this leads me on to the second part of my talk, where I want to tell you about the methods that's been put forward for doing this. And this goes by the name of dark sirens. Dark because they don't have an electromagnetic counterpart. Sometimes I also hear it referred to as statistical sirens, or just occasionally I've heard it called the galaxy catalogue method, which I think is like a very sort of dry name for something that I think is a really, really beautiful idea. So what is the idea? So when the LIGO, Virgo, Cagra detectors detect a merger, they produce this kind of sky map. Okay, and you might have seen this kind of thing before. It's a projection on the sky of what we call the localization region, i.e. where we think the event came from. And I've deliberately chosen an example here that's quite badly localized, just because it shows up better on a screen. Now, this information is two-dimensional. Sorry, it's two-dimensional on this plot, but in reality, we do have access here to a three-dimensional version of this information, and that's what's shown in the center here. So in principle, the Earth is sort of located in the center of this diagram, and these red woolly lobes are basically the 3D projections of these two-dimensional areas on the sky. So this is our localization volume. Now you can go point a telescope at that localization volume. And of course, what you'll see is that it's full of galaxies. There might be thousands or even tens of thousands of galaxies inside these lobes. But that actually results in something quite interesting. Let's say you know the redshifts of your galaxies, right? Which I realize is not a given, but let's say you have a survey or you do some targeted follow-up and you get the redshifts of these galaxies. That means you do actually know the redshift of your gravitational wave event, almost, because you know your gravitational wave event has to happen inside one of these galaxies. So so the redshift of your event will match one of these redshifts. Your problem is that you don't know which one it is. It's the needle in a haystack. You don't know which of your tens of thousands of galaxies is the true host. And the basic concept of the dark sirens method is that you are going to marginalize your gravitational wave data over every possible host galaxy within your localization volume. Okay, so let me explain in a little bit more detail how this works using some kind of sketches. I will leave aside the Bayesian formalism today because it's a bit too technical, and I'll just show you some results as well. And when we talk our way through this, it's often quite useful to have to hand the low redshift limit of the luminosity distance redshift relation. And basically at low redshift, that relation we saw on the previous slide, it reduces to Hubble's law. Okay, so the method, of course, applies more generally, but it's quite often useful to have this expression in mind to work out which way parameters are scaling. So what's the idea? You look along your localization patch of the sky, and what you will see in your galaxy catalog is some distribution of galaxies in redshift. Okay, and there'll be lumps and bumps in that structure. This big peak here might be some big cluster of galaxies, for example. Now you also have your gravitational wave data, and from that we get an estimate of that luminosity distance which sat in the gravitational wave amplitude. But our estimate of the luminosity distance is quite weak for most events. So we get some very broad posterior of where the event sits in this DL space. So what actually matches up a value of redshift to a value of the luminosity distance, at least in our simplified cosmology here, is the Hubble constant. So let's say we pick some value of the Hubble constant. Let's pick a low value, 45 kilometers per second per megaparsec. And let's say that value matches up the peak in our DL distribution to this particular point in redshift. Now, because this is a broad distribution, we can't just think about the peak. We sort of have to think about some sort of 2 sigma region of posterior around the peak. But what the dark Sirens formalism does, as I say, via a kind of formal Bayesian calculation, is it evaluates how much support is there from the galaxy catalog for the gravitational wave event to live between these 2 pink lines. Basically, in the simplest case, how many potential hosts are there to support this value of the Hubble constant? And you'll get some value from that. Okay, we can start building a posterior for H naught, and we'll start with our low value. Then if we crank up the Hubble constant, what we do is we slide these 2 scales past each other. So maybe now the peak of the gravitational wave data aligns with this big peak in our galaxy catalog, this piece of structure, this cluster. Now there's a lot more support for the gravitational wave event being hosted between these lines because there's a lot more host galaxies there. So we get stronger support for that value of the Hubble constant. And then finally, just to complete the picture, if we continue to crank up the Hubble constant, let's say 90 kilometers per second per megaparsec, it moves things even further. Maybe we're still kind of clipping the edge of this structure, so we get some intermediate value. I'm just making up the numbers today. And so what we've got out on the right-hand side here is some very loose posterior for our Hubble constant. How much support is there for different values of Hubble constant? And you can probably guess instinctively that for any one event and any one line of sight through your galaxy distribution, this measurement is going to be rubbish, right? It's going to be very loose, and it will potentially be biased or sort of pulled off course by random fluctuations in the large scale structure along the line of sight, right? If there's some big piece of structure nearby, that might kind of, pull you towards the wrong value of the Hubble constant. So any one line of sight is rubbish. But the beauty of the dark Sirens method is that you can throw all your data at it. So you can use all your lines of sight through your localization map. And not only that, you can use all your gravitational wave events, the whole kitchen sink. Okay, so you don't need to just cherry pick the best ones. You give it everything you've got, every vanilla binary black hole. And when you combine all that data, all those very loose individual constraints start to become a much more useful constraint. So let me show you some of the real world versions of the things that I've been sketching. So these are some plots that come from this paper by the LIGO-Virgo-CAGRA collaboration, and it comes from their sort of latest cosmology paper from the O3 data. So here we have the real world versions of the green and the red that I was sketching on the previous slide. So in green, here's the gravitational wave distribution for a particular event. In this case, it's 1908-14. And in red, you've got that sort of bumpy line, which is your galaxy distribution. Okay, and there's an orange line here as well, which is a particular weighted version of the galaxy catalogue. Don't worry about it today. Okay, so these things are real. Here are the real world versions of that posterior I was sketching for the Hubble constant. Again, just showing you two example events. And what you're seeing here in these sort of different blue curves, and please ignore the pink curves today. The blue curves are representing the different lines of sight through that localization map of the sky. So you see what I said is true. First of all, the posteriors for the Hubble constant on any one line of sight are really broad. And kind of even more so, you can see that the peak in this event here moves around quite considerably between different lines of sight. Okay, but nevertheless, when you combine all of this information and combining all the events in the LIGO O3 catalogue, here is the result. Here's the kind of headline result. So what you've got going on here in black is the standard siren measurement we saw previously from 1708-17. And in orange here is the dark sirens method. Okay, so this posterior. And then in blue, you have the combination of the two. And at first glance, you should be really impressed, right? With about, in the O3 catalogue, about half the events turn out to be useful. So it's not quite the full 90 events, it's about 45 events. But nevertheless, about 45 dark siren events appear to have constrained the Hubble parameter about as well as one standard siren. And if that were the magic ratio, 45:1, life would be easy, right? We would constrain the Hubble constant from the many, many binary black holes that we'll continue to get, and the job would be done. Actually, there's a subtlety here, which I need to tell you about, which means life isn't quite as easy as it seems. And that subtlety is lurking in this faint grey curve here. And this grey curve overlaps with the orange one mainly, except around the peak. So this grey curve is labelled in the legend as empty catalogue. And what that means is someone's gone and done a version of the dark sirens analysis, but with no galaxy catalogue information whatsoever. So what's going on there? How can we be constraining the Hubble constant based on what I just told you about how dark sirens work? And the answer is both kind of, good news and bad news at the same time. So this constraint is coming from the mass distribution of compact objects. Okay, so all the binary black holes and binary neutron stars we're seeing, their objects that are in those binaries are drawn from underlying populations. And we can try and plot what we think the mass distribution of that population is. Okay, and it results in a plot like this. Please don't worry too much about the y-axis quantity today. What we really care about is the x-axis, which shows the mass of the primary, the heaviest object in the binary. So at low masses here, you've got binary neutron stars between about 1 and 2.5 solar masses. Then there is a gap where we don't expect there to be any compact objects. And then binary black holes start from the objects that feature in binary black holes start from about 5 solar masses upwards. And they have some distribution here, which is not flat. It has some shape. There's a power law. We think there's some kind of break or peak feature around here. And then there's another gap sort of centered around 100 solar masses called the PISN gap, the pair instability supernova gap. And this is due to a particular sort of predicted instability in stars, where we think for really massive stars, they destroy themselves due to a kind of runaway instability. And so they shouldn't form any black holes in this range. Okay, so how is this constraining the Hubble constant? Remember I said earlier, what we actually get from gravitational wave data are redshifted masses. So the thing we detect on the left here is the true mass with a function of 1 plus redshift in front of it. So if the thing on the left is fixed, and the thing on the right here, the redshift is determined by that luminosity distance redshift relation for a given Hubble constant. So what's actually happening is if we change our cosmology, we change our Hubble constant, we change the redshift associated to this event. And if the thing on the left is fixed and the thing on the right changes, the other factor here, which is M1, also has to change to keep the thing on the left fixed. So basically, if we decrease the Hubble constant, we decrease this factor of 1 plus redshift, and therefore we push up the inferred value of M1, the mass, in the source frame. And if we continue to push far enough, we will push our masses into, for example, this upper gap. And because we don't expect to find any black holes in that gap, that value of the Hubble constant is then disfavored. Okay, and it's a similar story. If you increase the Hubble constant, you push things down into this lower mass gap. So the fact that the mass distribution has these breaks in, has these features, itself gives us constraints on the Hubble constant. And that's kind of cool. That's actually what's leading this gray line to constrain the Hubble constant very loosely, even without a galaxy catalogue. However, what it means is that when we do the full dark sirens method with a galaxy catalogue, we actually have to vary the hyperparameters that describe this mass distribution. Okay, because I've said these gaps exist, but their positions, their exact locations, the slope of this power law, these things are not known precisely at the moment. And they are all going to impact the cosmological parameter inference. So we really need to vary all of these parameters along with cosmology. And that has become, or that has been at least, sort of the holy grail of dark sirens research for the past couple of years, is to be able to make a likelihood pipeline that could evaluate all those parameters together. And that's something that has been very challenging because this is quite a heavyweight analysis once you've factored in all the gravitational wave data and all the galaxy data. I'm pleased to say a lot of progress has been made within the past year or so. There are various groups, including groups involved in LIGO, who I think are now ready to do this kind of inference. And so going forward in future, you may start to see kind of improved results, let's say, that constrain the Hubble constant using the full mass distribution and the galaxy catalogue information. And so you may see some shift and some change in parameters when we have new data. Okay, so that is the dark sirens method. As I say, there will be results forthcoming when the LIGO-Virgo collaboration starts its 4th observing run after some suitable delay. But the O3 result, which I showed you, is the sort of best one to date, but stay tuned for more. What I want to do in my remaining time, and this is, by the way, I'm pausing, it's a good point to ask questions if you have them. What I would like to do is tell you something about how we can use all this gravitational wave data to test the laws of gravity on large distance scales. Okay, but before I do that, I'll just pause briefly in case anyone wants to ask anything. If not,
I guess people are usually more comfortable asking in the end. Do you want them to start asking now, or?
No, at the end is fine. I was just, before I changed topic completely, if someone had a burning question or somebody was confused, I didn't want to move on, but at the end is fine.
Okay.
Okay, so we're moving on then to talk about tests of gravity. And the motivation for this is very well known. I'm sure you all know about dark energy, and that changes to our theory of gravity on large distance scales are one possible way that we might kind of explain cosmic acceleration. And so when we talk about testing gravity today, I'm going to be talking about things that affect the large scale structure of the universe. And I will be implicitly assuming that inside a galaxy, general relativity is preserved by something we call screening mechanisms. And what this means for gravitational waves is that we are going to be assuming that the production of gravitational waves, the actual dynamics of a binary, are unaffected. And we'll be asking what strange things can happen to them as they travel from a source galaxy to us, the observer. Okay, and this piece of artwork is by a UK artist called Penelope Cowley. She does all this fantastic art sort of based on science. And so this is her picture based on the LIGO observations. Okay, so everything I told you about dark sirens in the previous section can be brought to bear on this question of testing gravity. And in particular, we'll focus on tests of something called luminosity distances, or gravitational wave luminosity distances, sorry. So earlier we had this expression and we said there's the luminosity distance sitting in the denominator here. But what can happen in a modified gravity theory, and it's a very generic kind of common effect of modified gravity, is that this distance sitting in the denominator gets replaced by a new effective distance. And we call this the gravitational wave luminosity distance. And it'll be indicated by dGW on my slides. Okay, so we're not changing the true distance of the binary, it's still in the same place, but somehow the distance that appears in this equation has been modified. And so the sort of smoking gun then of modified gravity theories is that the ratio of the distance you get from your gravitational wave, dGW, and our normal luminosity distance, those two things are not the same anymore. And so their ratio is not equal to 1. And so what people have started doing is they've started building kind of model independent parameterizations of what this ratio might look like. Because if it's not equal to 1, it's most likely going to be a function of redshift. And so I'm showing you here one particular parameterization that has become very popular. It's from this paper here. It's some slightly strange functional form. All you need to see is that it contains a parameter called xi0, which I've colored in green. And if xi0 is 1, this ratio reduces back to 1, i.e. its GR value. So you can make plots of this functional form here just to kind of convince you that it's a semi-sensible thing to do. So here in the different colored lines, I'm showing different values of xi0. So when xi0's 1, the ratio is just constant. And if xi0 is greater or less than 1, you get some ratio which evolves with redshift. Okay, so we can do everything we did with the dark sirens analysis, but instead of constraining the Hubble constant, we're going to try and constrain xi0. So I'll skip all the methods. We talked about that before. I'll just jump straight to the results. Okay, so here is an initial attempt to constrain this parameter. And what you're seeing in gray are the individual posteriors from all individual events in the LIGO 03 catalog. And in red is the combined posterior. And at first glance, again, this looks really good. I saw this plot and I thought, fantastic, we've done it. We've constrained xi0. It's consistent with 1, its GR value. And the spread for 45 events is not bad. I was happy with this result. However, if you look closely, there's something funny going on again. So this grey curve here that spikes up, that really seems to be dominating the constraint. Okay, that's the thing that really seems to be killing off large values of Xi0. And if you go and ask which event is that, it's GW 1905-21, which was the one I said was the most massive confidently detected system to date. So how come that one system is dominating the constraints? Okay, and the answer is it's our friend, the mass distribution again. In the same way that if you increased or decreased the Hubble constant, you moved things up or down this plot. If you increase or decrease Xi0, you do the same thing. And in this case, what's happening is if you have a high value of Xi0, you're taking that event that's already very massive and you are pushing it into the PISN gap. And for that reason, there seems to be a sort of artificially strong constraint on Xi0. And so just as I said before, what we really need to do is to vary all those mass parameters along with the cosmological parameters and now along with the modified gravity parameters as well. Okay, so it's the same story. It's a heavy calculation. There are codes under development and you should see results on this in the next kind of batch of well, when there is data available in future from the next LIGO observing run. Okay, so this is a method, but it's not there yet. Sorry, with someone asking something.
I have a quick question.
Yes.
Xi0 is not very degenerate with H0 from what you said, because yeah.
It is exactly. And that's another reason, by the way, why you can't do a 1D constraint. So they both affect the luminosity distance redshift relation. And so in principle, you should vary them simultaneously. And that's kind of part of what you need to do down here with cosmology and modified gravity. Now, this might not have been a completely crazy thing to do if you say, I'm going to put a prior on my Hubble constant from, say, the Planck data. I care about testing modified gravity. I'm not worried about solving the Hubble tension. I will take the Planck prior. That would kind of help you a lot.
So you don't have expectations that you can actually constrain both of them with like good constraints at the same time, just with the dark sirens?
Not with the current data and not with the near future data. So in principle, you could. I'm just saying, I don't think you will need many more hundreds of events to constrain both well. Yeah.
Okay, thanks.
Okay, so that was kind of the modified gravity version of dark sirens. In my little bit of remaining time, let me sort of switch track and tell you about a different part of testing gravity. And I want to update you on the story regarding the propagation speed of gravitational waves. Because this was something that was very widely reported at the time of 1708-17, the standard siren, but there's sort of been some updates that I think are less widely known. So just one slide to remind people what happened here. So when we had the standard siren, what we got, as well as the gravitational wave signal, which is shown in the middle here, was a coincident peak in gamma ray flux counts, which is the start of the optical counterpart, or sorry, the electromagnetic counterpart. And those first gamma ray photons arrived within 1.7 seconds of the gravitational wave merger. And so the fact that these two signals arrive so close in time to within one another, you can convert that into a bound on any relative difference in speed between gravitational waves and the speed of light. And that bound, which has been quite widely quoted, is of order 10 to the minus 15 when expressed as a fraction. Okay, CT here, T stands for tensor mode, so CT is the speed of gravitational waves. Okay, and at the time, there was a lot of claims that this ruled out a lot of modified gravity theories. And in particular, what came under focus was a group of modified gravity theories called Hondesky gravity. And you should think of Hondesky gravity as like a parent theory, which has many kind of offspring. And it's basically the parent theory for all gravity models that have scalar fields in addition to a metric. So it's like a big sector of the modified gravity space. And the claim was that a lot of Hondesky models could not be consistent with this bound, and so they were eliminated. However, things got a bit more subtle the following year. And that was mainly due to some work by Claudia Durham and Scott Melville, who are just down the road from me at Imperial College London. And they pointed out the following thing. If you view this Hondesky family of gravity models as an effective field theory, an EFT, what that means is that there's a certain regime of energy in which your theory holds, and you're allowed to do computations with it, but that your theory also has what they call a cutoff, which is an energy scale above which your effective theory breaks down and you should not trust it anymore. And what these authors did was they went and computed that cutoff scale for Hondesky gravity, and they found it could be as low as a few hundred hertz when you express it as a frequency. So what that would mean that potentially, okay, the important point is that a few hundred hertz is below the merger frequency of the binary neutron star, which is about a few thousand hertz. So that still allows for models as shown in the picture here. So what you're seeing is the gravitational wave propagation speed, in this case squared, and you're seeing a bunch of models in which that propagation speed is below the speed of light in this kind of colored regime, so low frequencies. And then at this transition frequency, everything goes back to the speed of light. Okay, and there's sort of strong theoretical reasons that has to happen due to Lorentz invariance at high energies. And the LIGO band, the terrestrial band, is noticeably probing that high frequency part of the plot where you expect to find things traveling at sea. And it is not giving you access to this low frequency part of the plot where things might still be behaving differently. And so this question of whether the gravitational wave propagation speed is the same as the speed of light is sort of back on the table, at least at low frequencies. And so what can access low frequency gravitational waves? Well, there's the LISA satellite, which measures gravitational waves from massive black hole mergers. And PTA here stands for pulsar timing array. It's another kind of way of detecting gravitational waves. So suddenly things are a little bit more open again. So how are we going to move forward? How are we going to settle this question? And I'll just sketch you very briefly, and it'll be the last thing I do today, how actually, once we have LISA data, we might be able to answer this question again. And the way to answer this question would be to use particular kinds of special gravitational wave systems called multi-band sources. Multi-band sources are massive, well, okay, they are stellar mass black holes, but they are the heavier ones. So things of order above 100, or close to 100 solar masses. And those systems actually should be detectable in the LISA band, which is at low frequencies, several years before they merge in the terrestrial band. So the classic example here is the first ever detected gravitational wave, 1509-14. If we had had the LISA satellite flying 10 years before that, we would have seen that event at low frequencies. It would then exit the LISA band. So when it crosses this purple curve, it's invisible for some time. And then it would reappear when it crosses this orange curve to ground-based detectors. And what you can show is that if there is a change in propagation speed of gravitational waves between the LISA band and the LIGO band, what that will do to your gravitational wave signal is it will produce a shift in the coalescence time of the binary. Okay, and I'm skipping the calculation here today, but basically the time to coalescence will be changed from its GR prediction by this expression here. And if you have something that is, well, billions of light years away, even a tiny change in the propagation speed will produce a shift in the coalescence time of your binary by about 2 minutes. And that's something that we believe should be easily detectable once you have both the LISA and the LIGO or other ground-based experiments operating simultaneously. Okay, and just to kind of, there's a lot of detailed forecast plots I could show you, but the headline result is that with the low frequency LISA data, you can predict when a binary is going to coalesce to an accuracy of about 10 seconds. The LIGO, Virgo, Cagra or other ground-based detectors will come along and measure that coalescence time to an accuracy of milliseconds. So a 2-minute shift is really easily detectable. And what that will result in, and you can ignore all of these curves except the bottom plot here, is it will result in a constraint on that propagation speed, which is of order 10 to the minus 16. So putting you back in that regime of having measured the gravitational wave propagation speed to this super high accuracy. And that will be the way we will settle this question of propagation speed and whether we've ruled in or out Hondesky gravity all over again. Okay, I'm essentially at the end of my time, so I will just jump to my visual conclusions. I don't like texty conclusions, so what have we done today? We looked at the gravitational wave data that's in hand. We spoke about standard sirens and how they constrain the Hubble constant. I explained the dark sirens method to you and how that works. But we saw a really important part of that was that you needed to vary the mass distribution of astrophysical black holes along with your cosmology. And finally, at the end, I gave you an update on the story regarding this gravitational wave propagation speed and how things are suddenly a bit more uncertain, but we do know how to fix them when we have more data. Okay, I will leave it there and happily take questions, and thank you for listening.
Thank you so much, Tessa, for the amazing talk. So we now have time for questions. You can raise your hand, or if you're on YouTube, you can write the question down and I'll read it out.
I can't see any raised hands, so Tessa, if you can field the questions, that would be great.
Okay. Okay, don't see any. Okay. Okay. Felipe, go ahead.
Hey, can you hear me?
You're very low.
Okay, now can you hear me?
Yeah.
Okay. Tessa, thank you very much for this amazing talk. It's always great to hear you. So this a very general question, but have you investigated if the modified gravity may change the Schultz relation that we make for the standard science?
So can I just clarify, when you say the Schutz relation?
The relation between the modes that we use for luminosity distance that Bernard Schutz proposed in the paper. I guess it's in the beginning of your presentation.
Yeah, so I'm familiar with Schutz's work on where he actually proposes the luminosity distance of standard sirens as a constraint on the Hubble constant. It was the modes part I'm less clear.
Yes, on. yeah, but the relation between the modes that make you able to measure the luminosity distance, right? In the signal of the gravitational wave.
So that comes from, I mean, it's coming from the amplitude of your gravitational wave, the luminosity distance, right?
Yes, yeah. But modified gravity models may change this relation, or is it just astrophysical and it's blinded to exotic models of gravity?
So, okay, you're referring to a relation, and I'm not 100% sure if there's some kind of equation that you're referring to that I'm not aware of. Obviously, if you do have modified gravity, either either cosmologically or, you know, a strong field modification to gravity, it will change that wave amplitude, it will change the wave phase. And so you would need to do that, you would need to take that into account. However, conversely, that does mean even for a standard siren, you can do these tests of gravity that I spoke about with a standard siren, and people did try to do that with 1708-17. But because 1708-17 was very low redshift, the constraints aren't that great. Does that answer your question, or did I?
Yes. Thank you.
Before we take on the next question from Zoom, I want to read out a question that we got on YouTube. So that's from Jim Scare. How do you expect the uncertainty in H0 to diminish with more gravitational wave data? What choices do you make when you select the 45 events? So there are 2 questions.
Great. So for standard sirens, at least the constraint is roughly going to go down like root n with the number of events you have. Hence, you say, I need about 100 more to bring it down by a factor of 10. That would take it down from the sort of 10 kilometers per second here to 1 kilometer per second, well, per second per megaparsec, sorry. The reason that's only a ballpark estimate is, of course, it depends a lot on how distant your standard sirens are. And also how confident we are in associating electromagnetic counterparts to them. So 1708-17 was very clear that it was the obvious counterpart, but one thing that could really happen in the future is we get events where we see that there's maybe a counterpart, but we're not 100% sure it's the right one for that event. So that could cast a lot of doubt on things. But okay, broadly root n. For the 45 that end up being used in the dark sirens analysis, I'll struggle to remember all the details here, but I think for basically the other ones that are not used, one or more of the parameters is going to be sufficiently uncertain then due to the degeneracy between the parameters, it's going to impact all the other features of the binary. So if you have something that you think is eccentric, for example, which is very hard to measure right now, that might be making your mass or your distance estimates unreliable. And so that's why it kind of cuts out about half of them.
Thank you. We can now take your question, Isabella.
Hi, Tessa. Thanks for the talk. So I have two questions, if you have time. The first question is about screening. So you mentioned that you are considering, because of screening, that effects on the emission of the gravitational waves are not will not be as important as effects on the propagation. But some people also argue that the effects on the propagation, in the end, they end up depending only on values of certain functions at emission and the detection events, and that these effects will also be screened. What do you think about it?
Mm-hmm. For sure. So let me start by saying, you know, there's a whole other community of people whose research revolves around studying the effects of modified gravity at the source. So in some sense, what I'm doing is a little bit of an oversimplification. So I know the work you're referring to that says that basically there is an argument in particular screening mechanisms that basically wipes out the luminosity distance signal that I'm talking about. That proof happens in Weinstein screening, which is one of the major screening mechanisms. However, it's not completely generic, right? So a screening I'm using here is a general term that could crop up in different forms. There could be screening mechanisms we don't know about in modified gravity. And so even if Weinstein theories would not be kind of constrainable this way, the broader modified gravity space should be. Does that answer your question?
Yes, but but if you don't have any mechanism of screening, you have problems with I don't know, lunar laser ranging or something like this, right?
Right. So that's why we think that some kind of screening is necessary for sure. But, you know, really there are only two major screening mechanisms that dominate the literature, chameleon and Weinstein, up to a few other sort of variations on that theme. But there's no principle to say that's it, it's Weinstein, it's chameleon, or it's nothing, right? There is totally possible that there's some very, you know, we're not doing very well at constructing modified gravity theories. So if modified gravity is true, there may be some completely kind of new physics that we just have no, you know, no approximate of right now. And that could explain how things are preserved in the solar system in a way that's very different to chameleon or Weinstein screening.
Okay, I see. Thank you. And the second quick question is about these plots that you're showing. So we see that for different models, I guess, you have this cutoff frequency at which the speed of the propagation for gravitational waves is going to 1, and it's the same frequency for different models. And if it's not the same frequency, then won't you have a degeneracy between the change in the speed and when it changed when you use this method with LISA and LIGO? I'm not sure it was clear.
So at least the first part, let's tackle that. So the reason it sort of all happens at the same place on this plot is that, you know, all these curves are Hondesky gravity models, right? And if we say that Hondesky is an effective field theory, what we're doing is we're saying, at what energy scale do we believe other operators come into that theory that I don't know about? And that scale would sort of be this in the same ballpark, kind of irrespective of whatever the contents of your low energy theory is. So that's why they're all the same. I should say that this is a sort of estimate based on, as I said, like considering when new operators could come in. There could easily be coefficients of order unity in front of that. So it's not an exact prediction, it's a ballpark prediction, if that makes sense. I've forgotten the second part of your question already.
So the second part is you're using LISA, you're comparing what you get from LISA with the terrestrial interferometers, right?
Yes.
To measure these difference of that, to measure the speed, right? The difference to 1. But if you have, if you vary the frequency, this cutoff frequency, or if you vary the speed, won't you have the same effect, like the same kind of delay in the signal?
So there is definitely more than one parameter describing this transition, which I think is what you're saying, right? There's the height of the transition, then there's the frequency at which it occurs. And if you have some kind of smooth thing like this, there's even a width to that transition. And those parameters will have some degeneracies for sure. And in some other work, we have studied how well you can measure all those parameters together. What we do in the result that I showed you is we actually make it a sort of infinitely sharp step, but that's the most conservative case, because if you have a broader step, although it will have some correlation with your speed bound, it'll actually make your speed bound tighter because you'll see more significant effects leaking into the LIGO or LISA bands. So parameters are correlated, but it doesn't undermine the measurement, I think is what I'm trying to say.
Okay, thank you.
Are there any more quick questions? Tessa, I actually have a few questions. Do you have a few more minutes, like 3 more minutes?
I do, yes. I don't want to keep anyone else too long because I know I've run over the hour, but I can stick around. Okay.
So I don't know if we end this or if I'm just gonna ask them quickly. So I'm curious, in the plot that you have, like the third one, so this is your Z, or are you plotting N of Z?
Sorry, am I plotting what or N of Z?
Is this the redshift, or is this the redshift distribution of
So
the galaxies?
I should say, first of all, that this is, very obviously just a sketch, but this is meant to be n of z.
Okay.
So yeah, this is not one galaxy with a very weird redshift distribution. This is the number density of where they are. So this is a cluster and this is a void or something.
Is it very relevant to point out exactly which galaxy it's coming from, or is this information not as relevant as it might?
Yeah, that's not super relevant. And that's kind of one of the beauties of the method of why Dark Sirens works. We do not see every galaxy in the universe. So we know there are missing galaxies. It doesn't matter if we don't see the true host, as long as there is structure near the true host, then we still get the right redshift information to do the result. So yeah, that's a lifesaver and a good point.
Okay, I'm just having a hard time like picturing this whole 3D thing, and then all of your redshift shells, and then the various galaxies distributed and like pinpointing like which direction. But it seems extremely cool. Isabella, do you have another question? You still have your hand up?
No, sorry, I forgot to take it off.
Okay. I guess any other questions we can chat about it personally soon. Okay, so if there are no more questions, let me just take a quick look at YouTube again. Okay, we'll wrap this up. So the presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a very special thanks to you, Dr. Baker. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar.
Thank you very much for all the questions, everyone. It was great to meet you all.
Thank you.